Now we're going to look at how to develop confidence interval for population mean mu, unknown population mean mu, under the condition that the population standard deviation is known to us. Okay. And here is the formula. Once again, remember, the generic formula is you start with the point estimate of the population parameter for which we want the confidence interval. So we want here confidence interval for population mean mu, which is unknown. So you start with the point estimate for mean mu, which is x bar, then plus or minus the critical value, and the critical value comes from the probability distribution of x bar, the point estimate. And what is the probability distribution for x bar? Well, the probability distribution for x bar is normal distribution. Okay, of course, for that to be true, okay, you have to appeal to the central limit theorem. So there are two conditions to the central limit theorem, as we saw in chapter 7. If the original population is normal, then x bar will be normal, no matter what. Doesn't matter anything else. Okay. But if the original population is unknown, or it is not normal, or we don't know what the distribution is, then we have to make sure that the sample is large enough, greater than or equal to 30. I would say greater than or equal to 30. So in which case x bar, the probability distribution for x bar will be approximately normal. In fact, it will be very, very close to normal when n is greater than or equal to 30. So we can safely use normal distribution. So that's where this z comes from. Okay, and then this subscript alpha over 2, I'll talk about this subscript in just a second. And then the standard error of x bar. Standard error of x bar is sigma over square root of n. And since under this scenario we are assuming that sigma is known, then we can plug in the sigma value and the n value, and we will have our confidence interval. Okay. Now going back to the z, what is this subscript alpha over 2 tell us? Okay. Now this notation or this convention is true for all the probability distributions, whether it is normal distribution or some of the other distributions that we're going to talk about, like t distribution, chi-square distribution, and f distribution, and so on. So the subscript, after you specify the letter for the probability distribution, the subscript always refers to the probability to the right side of that value. So z sub alpha over 2 is the value of z such that the area on the right side of z is alpha over 2. Okay. Now why is z sub alpha over 2 here? Okay. Here once again, remember, what we want is 1 minus alpha confidence, which is 95% or 99%, and that is going to be the area between the lower and the upper limit, which is in the middle part of your normal distribution. Okay, so that's 1 minus alpha. So which means what's outside the middle part, contained in the two tails together, is alpha. So each tail is going to be worth alpha over 2 in area. So the upper tail is alpha over 2, the lower tail is alpha over 2. So if you want the z value corresponding to our 95% or 99%, the 1 minus alpha confidence interval, then the z value here is going to be such that area to the right, that is only one single tail, so two tails put together is alpha, one single tail is alpha over 2. So area to the right of z is going to be alpha over 2. That's the reason why we use z sub alpha over 2 here. So z sub alpha over 2 will come from either normal distribution table or our norm.inv function in Excel, such that area to the right is alpha over 2, which means the cumulative area is what is listed in the tables, right? Cumulative area is going to be 1 minus alpha over 2. Alpha over 2 is to the right, so to the left, which is cumulative, is 1 minus alpha over 2. So here let's look at the example here. So if you want 95% confidence interval, so the middle area is 1 minus alpha, which is 95%. So outside will be 5% or 0.05, which is divided equally between the left and the right side. So if you want this Z, the area to the right is 0.025, so that is Z sub alpha over 2, which means the cumulative area is 0.975, and for 0.975, if you go to the table and read the Z value, you will find that that is 1.96. Now the corresponding Z value on the left side is going to be, since this is a symmetric normal distribution, the corresponding value on the left side is going to be simply negative 1.96, which is this tail area of 0.025. Okay, on the right side is 0.025 is 1.96. On the left side, the left tail area of 0.025 will correspond with minus 1.96 for Z. Okay, and here are some more Z values for different confidence levels, and 1 minus alpha and so on. So an numerical example, suppose we have a sample of 11 circuits from a large normal population with a mean resistance of 2.2 ohms. We know from the past testing that the population standard deviation is 0.35. So this is a sample mean, and sigma. This is from past testing, the population standard deviation is 0.35. Now we want to develop 95% confidence interval. So we start with X bar, which is 2.2. That's our sample mean. Now Z for 95% is 1.96, as we saw in the previous slide. Then sigma over square root of n will be 0.35 divided by square root of 11. Now this part of the formula gives us the margin of error. So we can say our estimate for the population mean resistance is 2.2 with a margin of error of 0.2068. In other words, the mean will be between this lower limit and this upper limit with a confidence of 95%. Now let's look at this example in Excel.